In any case, let's get back to this. Draw the major organic product with this ester when it reacts with each of the sets of reagents. Okay, so this is actually going to be fun because what we're going to do instead is identify the chemistry in this molecule. So we're going to start with Austin. Why not? What chemistry do you see in this molecule?
I see a double bonded oxygen, carbonyl.
Pause. When I say identify the chemistry, what do I mean, Monique? That's part of it. John, when I say identify the chemistry, what do you think I'm fishing for?
For like acid base and nucleophile on the product.
You want to take a swing again, Austin?
Well, your oxygens have electrons around them. Therefore,
Okay.
let's say that carbon bonded to the oxygen.
Okay, whoa, let's pause. So you've told me to draw in lone pairs. Absolutely agree. Yes. Let's get lone pairs on, and then you immediately shift to carbon. Okay. The goal here is to identify the chemistry possible for this molecule. Adding lone pairs, absolutely a good idea. We can now see the electrons that could potentially act. Okay. Now jumping to every other atom is a bad idea. Once you've identified a site for potential reactivity, nail down what that reactivity is first. Okay? So, oxygen, what do you want to give me? Cool. So when we see those oxygens, we're referencing those acting as bases. Good place to start. Bian, do they have the same base strength? Cool. Let's just continue the loop. Georgiana, which one's the stronger base?
I would say the carbonyl.
Kiefer, why is the carbonyl base number 2 the stronger base?
Because it has pi electrons in the pi bond that can move.
Cool. Louis, what word would I have liked to have heard Kiefer say? His description was lovely, but I wanted to hear a word.
You said pi electrons. Is it something that is different from that, or is it because it has a double bond, you mean?
Yep, he said double bond, and he mentioned pi electrons. All of those are multiple words.
Okay.
I wanted one word.
Strong.
No. It's okay.
Okay.
Jocelyn, you got any ideas?
No.
Is it useful that there's a hint up there with the arrow? Jocelyn?
Is it equilibrium?
Nope. Skyla? Yeah, we're looking at resonance. Okay. So what Kiefer was referencing is that pi bond can resonate, giving me that negative charge, whereas the oxygen could also resonate. The other oxygen could also resonate. Couldn't it, Aiden? Yeah. Malia, what would happen to that oxygen if it resonated? Our blue oxygen. It's okay. Paige?
Wait, you're asking if the blue oxygen resonates?
Yep. Well, let's switch that a little bit to be a little bit more helpful. I'm not asking if the blue oxygen can resonate. I am stating the blue oxygen can resonate. I want to know what happens to the blue oxygen when it resonates. Megan?
Does it become like a negative charge or becomes...
Megan, you got the right idea, wrong direction. Rolanda? Nope. If it comes off, it's not doing resonance, so that we're then breaking sigma bonds. Cody?
Yes.
What happens when it resonates?
The oxygen becomes positively charged.
Those electrons resonate inwards. What do we end up with? Be positively charged. So if we go all the way back to Kiefer's statement, with the pi bond electrons being there, what he's referencing is that those pi electrons could move through resonance, which could be used to stabilize, if we wanted to, the conjugate acid. We could also use that resonance to see that that oxygen becomes negatively charged. A negatively charged species should be a stronger base than a neutral charged species. Okay? One of the things that was neglected to be mentioned was that oxygen, the blue oxygen, also has a resonance potential. Okay? But if it resonates, what happens to its lone pair electrons? They get occupied into the pi bond, meaning that oxygen carries a positive charge. So if we're asked back to that original question, is there a difference in base strength? Yes. The base, or B2 as we're calling it, the carbonyl oxygen, is vastly more basic than our ester oxygen because of all that resonance system. Okay? Kind of makes sense? Cool. So let's backtrack out of all that. Emily, can you define base for me?
Something that shares its electrons with another.
Donates electrons officially to H plus or to a positively charged hydrogen as a nuance behind that. Typically, we would memorize proton donor. That really only works if we're seeing the chemical reaction. We haven't even talked about a reagent yet. All we're trying to do is say what chemistry is available to us. Does that make sense? So, awesome definition. Thank you. So we've got two potentially basic sites. Sarah, what charge is your base typically? Partially negative becomes a good signifier. That can help us out when we're looking for our lone pair electrons. That's why our oxygens were great as potential bases. Make sense? Okay. Caesar, what other chemistry do you see?
Well, okay, I have a question real quick.
Yeah.
So between both of those oxygens right there, is there a partial positive on the carbon, or would it not be? Because they're both oxygens, so would they exert the same electronegativity?
So is there a partial positive there? I guess you directed that at me, so I guess I get to answer that. Is that fair?
Yeah.
Yeah? Okay, just checking. Okay. Yeah, there should be a partial positive there. I completely agree with you, and we'll come back to answer the follow-up question. But first, Lauren. Why is there a partial positive there?
I mean, he said something about how there's two oxygens. So it would like make the carbon.
Okay, I'll accept that, but I am going to follow up back to you. What reactivity principle, okay, are you using to classify that there's a positive oxygen or a positive carbon there? So if you're going to use that definition and say there's two oxygens next to it, what are you relying on to say that that is partially positive? You can say you don't know. It's okay.
The electrons?
If it's positive, it doesn't have any
Oh,
electrons.
wait.
Pause. Monique, what do you think I'm referencing? Right idea, wrong thing. What's the group of those systems? What's the first one? You can say Cario, fine. Charge, size, electronegativity, resonance, induction. So in the argument that you guys have both pushed, that carbon should be positively charged because of the electronegative oxygens. Which of those 5 rules are you using to say that that carbon is positive?
I just heard it. Is that right?
I heard nothing. Induction. Yes, you're using induction. Induction is rule 5 on our list. That's the bottom of the barrel. Okay? While it is possible to use induction as an argument, okay, every single time you use it, what am I going to ask? Is there something higher on the list you should be using to evaluate first? Okay? So we could start. We're looking at that carbon. Is it charged?
Well, I think that's why Caesar asked, like, would resonance work for this? Because you're stabilizing it again through resonance.
I didn't hear Caesar say anything about resonance.
Okay, I'm pretty sure that's what he was asking.
What I heard was that is that carbon positive?
And you
Okay.
said,
And because of the withdrawing effect of those oxygens. So what I wanted to do is to clarify that system. So we'd start with, is that carbon formally charged?
No.
No. Okay. Is carbon large?
It's not as large.
Because we're looking at size. We don't really have any size comparisons to look at in that case. Okay. Electronegativity, not particularly relevant. What we're looking at is how the electrons could potentially move away from that carbon. So the atom effects are useless. Before we get to induction, we first have to shoot spider webs. Resonance. Is there a resonance system that we should be looking at before we evaluate induction?
Yes.
Yes. There is resonance with those pi electrons making that carbon positive. So to your statement, is that carbon partially positive? Yes. Why? Resonance should be your explanation. We're going to push on that harder in just a second, but now that you've identified that that is a positive carbon, I see you, I'll come back to you. Which one of our reactivities do you think you see on that carbon?
Like, what do you mean?
Acid, base, nucleophile, electrophile.
Well, since it's positively charged, would it be electrophilic?
Looking at as electrophilic, and would argue you already brought in kind of the cheat that we were looking for. With our base, we said we wanted to see a partial negative charge. What did we want to see for our electrophiles? Positive charge. So you bring in the cheat effectively with that. That's good. Okay? Austin?
And with the two oxygens being connected to the carbon, is it causing that partial positive, that carbon to be more positive because of them both withdrawing?
Okay.
I know.
Interesting question. So Austin's now asking, is that carbon more positive?
Causing it to be a good electrophile?
Is it more positive than that carbon?
No.
No. Okay? So more positive becomes a very challenging question. How does that need to get refined, Cody? Because it looked like you might have an idea on that. His question's too broad. Do you have any ideas how you would modify that question?
I don't know.
It's okay. John?
Maybe you could compare it to ketone.
Ah, there we go. Because we just studied the chemistry of carbonyls, ideally, I don't know what that word was supposed to be, our ketones or our aldehydes. Okay, what you could be starting to reference is say, hey, I just learned about that carbonyl chemistry, and that carbonyl was electrophilic as well. That was a partial positive. Okay? Is it going to be important for me to know the difference in the reactivity of those carbonyl carbons? They're both carbonyl carbons, but one belongs to a ketone and one belongs to the ester. Should I know the difference in reactivity? Yeah. Okay. So what's your initial assessment, Austin? Which one is more positive, the ester carbonyl or the ketone carbonyl?
Which one's what again?
Which one is more positive,
Positive?
more electrophilic?
I'd say the ketone. I mean, I'd say the ester because it's got more.
Okay, I'm not asking for a right or wrong. I just asked which one was more positive. You're saying the ester.
Stay with the ester.
Okay. Bayan, what rule do you think he's using to say the ester is more positive than the ketone? Kiefer, you got an idea?
Wasn't there like a chart in one of the lectures, like
Fair play. I'm going to object, of course, but absolutely fair play. Is there a chart that shows the reactivity of these individual carbonyl compounds? Yes, if you've memorized that chart, you know the answer. Okay? Did anybody memorize that chart?
No. Well, I didn't.
So, you can decide right now, hey, notes, I got a chart. There's a chart that ranks carbonyl compound reactivity. I should probably memorize that chart. Okay? If you don't want to figure out the why, the how, the build, all of that, that's okay. You need to memorize that chart. It exists. Okay? That will work phenomenally for multiple choice questions. That will work phenomenally for the final. What it won't work for is the practice exam 2, or not practice exam 2, the retake on exam number 2 coming this Wednesday, because this Wednesday is show your work. I want to see an explanation behind it. Okay? Do you understand the content? Okay? It will absolutely work for the multiple choice on exam 3, and it will absolutely work for the final exam. Okay? But you have to be able to have it memorized for both those systems. For both the retake and for the show your work on the next exam, that's not going to fly. You have to know the why. Okay? That why is boiling down to the exact same thing that we've now used multiple times over. As so Monique so eloquently put, how do you want to call it? Cario. Ah, it hurts every time. I didn't teach Cario. I said there's an acronym that says Cario, and it's stupid because it doesn't explain all of the individual steps.
We just watched you do it this weekend.
Does any update upload a video or something?
Do I have to delete a video then? Charge, size, electronegativity, resonance, induction. You need to be cognizant of those pieces. Okay? For the sake of the class, you can get out of the class ignoring all of that. That is the only part of the class that is directly relevant to every other place that you could possibly move. Okay? Pharmacy, dental, health, PA, medicine, vet. That ranking system is what's used to predict the chemistry of individual molecules that you would encounter in the future. Okay? Knowing the chemical reagents is utterly useless. Okay? Even the reactivity limit is useless. Knowing how to apply a given rule set to a new system is very important. Okay? So, good answer. Of course, it sidetracked me. Absolutely fair play. No one had it memorized, though, so it doesn't work. So we need to use something else. We need to use something that we've been using every flippin' day that we've moved into this class. What part of Cario is Austin invoking to say the ester is more positive than the ketone? Induction. And what did we just say about induction? You've got to evaluate all the prior pieces first. Okay? This case is a little bit better to reference because we now have a legit comparison. You're comparing the green carbonyl carbon to our purple carbonyl carbon. We would start with charge. Fair play to say that. Is the charge different, Malia? So, and this is something that might be confusing. When you see charge, well, are we talking about partial charge? No, we're talking about an explicit charge. Do you see a negative or a positive? They're the same. Okay, so charge isn't relevant. What's the next thing you move to, Megan?
What?
What's the next thing you move to after charge?
Hold on. That was really on the spot.
That's okay. Don't stress. We can shift. Rolanda? Size. Is carbon different from carbon in size? Megan, we'll go back to you. Is carbon different than carbon as far as size? No. You got confidence. You got it. No. Okay, what comes after size, Sarah? Electronegativity. Emily, is carbon different from carbon as far as electronegativity? Skyla, what comes after, I don't know, size? Electronegativity. Electronegativity. Resonance. Jocelyn, is there a difference in resonance for these two molecules? One of those answers is correct.
Yes.
Yes, okay. What's the difference in resonance that you see? Louis, sorry, I followed.
Oh, me?
Yeah.
Sorry.
What's the difference in resonance that Jocelyn sees?
One has it and one has not.
False. They both have resonance.
Oh.
Georgiana, what's the difference in resonance?
One has like two oxygens, one has one.
That's the difference in the atoms, which will lead to the difference in resonance. Can you elaborate the difference in resonance yet? Bayan, Georgiana said the ester had two oxygens, the ketone had one oxygen. What is the difference in resonance? Kiefer, full circle.
Is it with the lone pairs?
I need a little more.
Oxygen has lone pairs, and on the ketones, the oxygen is only with lone pairs. On an ester, there's two oxygens with lone pairs. So they can do resonance that way.
You're just telling me there's a bunch of lone pairs.
Lone pairs?
I want a little bit more than that. I'm positive you know what you're talking about. You just aren't saying
They're
it.
conjugated.
We have a green arrow. We can move a lone pair from that second new oxygen that is unique. We can move that in to make a pi bond. As we move that in, that can shuttle the other pi bond out. Does our ketone have that extra resonance?
No.
No. So that's our unique resonance. Okay? The ununique resonance, we could show in blue here. That ununique resonance is what's generating our positive charge on both of those carbonyl carbons, yes?
Yes.
Cool. The ester has that green arrow. What does that green arrow do to the strength of the positive charge? That lowers the positive charge. We've brought electrons in to stabilize that positive. What does that lead to, Lauren? What's our final conclusion with that? That's hard. There's lots of moving pieces. What's our final conclusion?
About the resonance between the ester and the.
Why were we even looking at resonance? We're holding lots of thoughts. It's okay. Austin, it was your question.
I know. I still don't know the answer to it.
What was your question?
Yeah, wait, read that one.
The question was, is between the ester and the ketone, because the ester has two oxygens bonded to the carbon, does it make it more positive
No.
versus the ketone?
No.
What is the ester oxygen doing to the positive charge? It's neutralizing it, which means the ester positive is weaker. It's less positive. Weaker than the ketone, which is really important. Because if we remember all the way back, because Austin asked the question, and actually I must have kept pushing on you, and I said to tell me which one you think is more positive.
I did, and I kept saying that the ester was.
And you said the ester, because what was our reasoning? Induction. Induction is at the bottom of the barrel, resonance is before it. We needed to look at resonance before we evaluated induction. This is such a common manipulation, if you will, that you will explicitly see questions like this that the vast majority of students will get wrong because they start applying induction to it instead of resonance. We have pushed resonance for so long, forever, that you should be using resonance. Right? Why does no one want to use resonance? Any ideas, John?
Maybe it's because it can be a little bit of a boost of the system, making sure that everything is following all the rules and all the octets and making sure that your electrons move towards electronegative elements, all that stuff.
So there's a bunch of extra rules associated with it. Lauren, since your mouth was moving, maybe that was the sound I heard before I asked John, why do you think no one uses resonance? There it is. Nobody's got time for resonance. That's okay. You can establish that you don't have time for resonance. You also don't have time to pass the test. Yeah. That's, yes. What's that? Yeah, that's the intent. Okay? You all have the ability to do resonance. You're trying too hard to move too fast. Slow down.
Wait, but you said that if we slow down, we don't have time.
No, I said if you slow down, what happens? You get the answers right. You may answer fewer questions, but all the questions you answer are correct.
Quality over quantity.
And right now, based off of what I've seen, what we're pushing for is quantity
Okay.
at a huge loss to quality.
Okay.
Okay? You need to slow down. You need to accept that you have to draw. Okay? You have to draw things out. Yes, sir, Caesar.
So for the test on Wednesday, is it going to be normal test length or is it going to be shorter?
Fair question. Our Wednesday, I've been telling some people, I don't know why I decided to letter it, but I freaking lettered the questions. I think there's K questions. I apologize. Yeah, someone counted out. It's 10, 11. It's somewhere in that range.
13 is N.
Oh, okay.
That's the middle.
Wait, so there's only 12 questions? Okay.
They are all, for the most part, short answer. Some of those questions are kind of, I think there's some that actually have multiple choice answers. I'm not positive on that, though. There are for sure questions that I pulled straight out of the multiple choice and said, you know what, I'm going to delete the multiple choice and you explain this to me. So, yeah. And I would argue you're looking at everything, beginning to end.
Beginning to end of what? Like organic chemistry?
Organic chemistry. Organic chemistry is a full year course that has been arbitrarily cut in half.
A spark sheet, like just one sheet, just spark notes. No, I just need it.
No.
Wait, what happens if we do not well in this one?
So here's, bright side. If you don't do well on the retest, I will not take points away from you.
But you won't give us
It's
it.
basically just a help.
It's to help your exam too. You need help.
You sound like a therapist.
Like what?
I hope I don't.
Organic chemistry therapy.
Your therapist should hopefully talk much nicer to you than I do.
Does this replace the curve?
Yes.
So there's no
What?
curve.
So you said rather have
The test.
With this exam, you don't want a curve.
No.
Yeah.
Oh, because
Because the exam is bad enough that I would just say no.
Can we just forget about this?
Nope. This content shows up on the final. You need to know it for the final. This content shows up in this unit. You need to know it for this unit.
So are you not, I have a
So.
question. Are you just not showing the exams because you just did so bad? Like, I want to know what we messed up on, but how are we supposed to know if we don't see it? Did we just do bad?
just on everything?
Yeah.
Okay.
Do you need us?
Slightly.
I'm kidding.
Unfortunately not.
He loves
Sarah?
Is there a spectroscopy? I can't say it.
Spectroscopy.
Please no.
You are responsible for spectroscopy.
Okay, so I'll read these.
I think that's what he meant.
You are responsible for spectroscopy. Spectroscopy was officially on the past exam. And if you look at the lecture sequence, I think it was the second lecture video was spectroscopy. So,
the Degree Center, there's a little paper perspective.
I get back to the question.
Yeah,
Cool.
So if you said there's K questions on it,
that's 12.
that's 10?
No, it's
No, it's
12.
11.
I don't know.
What?
I feel like that's a lot of the questions.
Maybe we should
There's
retake
26
Oh,
letters.
Yeah.
Wait, so it's only 11 questions.
I was doing the Spanish on.
Okay, so we have
So-
an electrophilic site.
We have an electrophilic site. We have 2 basic sites. Is that all that we have? No? Why not?
We have an acidic hydrogen.
Where do we have acidic hydrogens? The what?
The top of like pentagon.
Oh, top. Okay, I get you.
I was trying to figure out.
That hydrogen, okay, is more important than all the other hydrogens. Why?
Acidic.
It is acidic. Why is that hydrogen acidic?
Because the resonance electrophilic.
Because of resonance. Oh, you mean we've got to use resonance yet again to explain this reactivity? Yes. Yes, we do. Okay? Okay. What are you talking about when you talk about resonance? Because when I look at that, I see no resonance. Because if I'm going to try to move electrons, I would have to move the sigma bond, and I'm not allowed to move a sigma bond in resonance. So I'm a little puzzled by your statement of resonance for that acidic hydrogen.
Well, because it's acidic, the hydrogen comes off as H plus. And then we get resonance from the electrons.
You get resonance from the, sorry again?
From the electrons.
What electrons?
The lone pair. The leftover lone pair from the.
That leftover lone pair found on what structure? Don't tell me the structure I just drew.
That's it. What do you mean?
Emily, do you know what I'm talking about?
You asked the question. When you
Where do I find the lone pair?
when you like take off the hydrogen, so, like in the bond between the
No, we're fishing for a term here. Fudge. Well, there that went.
Okay, there we go. I think
What are we looking for?
conjugate.
Conjugate base. If we're talking about acidity, we look at the strength of the conjugate base. That's a negative carbon. Negative carbons are not stable and cannot stabilize a negative charge. Why is that hydrogen acidic? Because there's a resonance contributor where we can put the negative charge onto an oxygen. What we're looking at is the acidity of the alpha hydrogen to the carbonyl. So that when we look at an ester functional group, we should see the potential for 2 base sites. As we talked about, were both of those base sites equally basic? Nope. We said the carbonyl was the most basic, which means we could probably eliminate that from our reactivity. We talked about the carbonyl carbon being an electrophile. We talked about the alpha hydrogen being acidic. Okay? What you are doing by just looking at the functional group is trying to identify all of those pockets of reactivity. Why? If I think my carbonyl is basic, what should I look for as a reagent? An acid. I guess I didn't say a name. Thank you, Austin. Okay? Because bases react with acids. If I look at my carbonyl structure and I see that electrophilic carbon, what should I look for as far as a reagent, Caesar? A nucleophile. Okay? If I've been listing out my reactions, okay, and my reagents as they're called upon within the lectures, I can now start to group some memorization of what things show up where and when they are particularly relevant, as opposed to just shotgun memorizing everything. It provides a framework on which you can now hang some of that chemistry. Kind of, sort of?
Kind of, sort of.
Cool. As we went through and did that, we started to call attention to some things that were particularly useful, and then I kind of got tired of it. Okay, but acids donate H+. So what are we looking for? You're looking for H+. Bases donate electrons. What were you looking for? a negative charge. What do nucleophiles do?
They,
Donate electrons. What am I looking for, Emily? To find a nucleophile. Thank you. That's why I re-asked the question. And our electrophiles, thanks to Caesar at the very beginning, positive. Okay? If we know our definitions, we can then start to recognize where those things, where those charges appear so that we can predict our reactivity. That's the point of those definitions. Not to just regurgitate them, but to overlay them now on structures. Some of that becomes obvious when we draw in lone pairs. And we go, oh, well, we've got oxygens with electrons. Okay? Some of that is obvious or should be obvious because we see pi bonds, and pi bonds can resonate, generating multiple charges. Okay? That's why all of that content was discussed in OChem 1. And all we're going through and doing is creating a new functional group for you to look at and say, okay, what could it do? What could it do? Kind of, sort of?
sort of.
Yes, John.
Could leaving group be considered like a class of activity?
That is a fascinating question. Because if we go through and look at our esters versus our ketones, what is the primary difference between those?
It's the oxygen connected to the carbonyl versus just another carbon.
Really what we're saying is that that atom in the green box has changed. Does that atom affect the carbonyl? Yes. Jocelyn, how does that atom, in the case of the ester, affect the carbonyl?
Where?
Over here. The ester green box. How does that oxygen affect the carbonyl?
Can you pass it to someone else?
Okay, Skyla? Say that again. You're right. It does make the carbon less positive, but you asked like 2 tiers of a harder question. How is it making the carbon less positive? That's what I wanted to hear. There's a resonance potential. That atom X has resonance, which stabilizes the electrophilic carbon. Okay? That's why our chemistry is different in this unit versus the past unit. Atom X has the potential to stabilize. It could also destabilize. That's what the rest of the unit is talking about. What happens if instead of it being an oxygen, it's another oxygen? Well, that was stupid, Mike. But what if that other oxygen had something else going on with it? Could that change it? I don't know, maybe. Let's look at drawings. Let's add more structures into it to see how that can stack and affect. Okay? Why did we talk about that? Who asked that? That was John?
Yeah, I was asking if leaving groups could be considered.
Thank you. Yes, that's all I needed. Okay? So if we go back and, not that eraser. Okay? And if we go back and now look at that atom X does have this resonance stabilizing effect. But if we push on this reaction a little bit harder and we think back to how we reacted our carbonyls, okay? With our carbonyls, we took nucleophiles and we reacted them. We still have a carbonyl that could react. How does that difference manifest one layer further down? Okay? Well, when it reacts, it goes through and it forms our tetrahedral intermediate. There's our hydrogen, there's our OCH3. There's a negative, there's their goofy ring. Okay? In the case of our ketone, what happens? We stall out. There's really nowhere for those negative electrons to go. If they tried to go back down, we would exceed the octet and we'd have to kick something out. Okay? If we kicked out hydrogen, well, we go backwards. Okay? But it's a little bit worse than that. We're comparing hydride, what we started with is our reactive negative, and we're comparing that to what, Megan? What are we comparing that to in our product? It's a bit of a challenging one. There's no positive hydrogen. Cody, what are we comparing it to? What are we comparing that negative hydrogen to in our reactant?
Partially negative carbon.
No. Lauren, you got an idea?
What was your question? I'm sorry, I blew my nose.
You're fine.
I can't breathe.
You should breathe as a priority. What are we comparing that negative hydrogen to?
It's a negative oxygen.
Thank you, Lauren. We're comparing it to the negative oxygen. Why? Ooh, that's a fun question. Why would we compare the negative hydrogen to the negative oxygen? When we look at a chemical reaction, what do? We compare our reactants to our products, and we look for the most reactive thing on each side of the equation. If our products are more stable than our reactants, what happens? A reaction happens because the products are more stable. If our reactants are more stable than products, what happens? Nothing. Okay? Or very little happens because our reactants are more stable. So trying to predict a chemical reaction is looking at the most reactive things and saying, which one's more stable? How do we decide stability? Austin? Charge, size, electronegativity, resonance, induction.
Yeah.
I appreciate the salt money. Okay? We do that every single time for every single reaction. Okay? We use it when hydrides react because they form negative oxygens. That's why hydrides react. It forms a more stable thing. That one's usually pretty straightforward because hydrides are stupid strong nucleophiles. Okay? They aren't stable, so they react immediately. If we go through to the ester and it reacts, we're looking at that H minus going through to that reaction. I want an O minus. O minus is more stable. But now John has brought up an interesting question. Could that O minus come back down? It could have come back down in the other case, but what would have happened? It exceeds octet. And it exceeds octet, so what could it spit out? H minus versus H, that's not really useful. C minus versus H minus, they're both pretty freaking reactive. Like, that doesn't sound particularly good. Oh, but O minus is pretty stable. So what are the choices? Well, I either keep O minus or I form more reactive things. I'm going to stick with O minus because that's the least reactive of all those options. When we go over here, O minus, what could it kick down now in our ester? I'm away from the recording. That was stupid.
Wait, what?
If we look back now at our ester, I'll have to point with my little pointer. There it is. There's my ester now, right? My little arrow?
Yep.
The O minus, the electrons come back down. As Austin suggested, we would exceed the octet. We also exceeded the octet when we looked at the ketone. And we said, what could happen? I kick out H minus. H minus for, oh, that's a bad idea. C minus for, oh, that's a bad idea. What happens when I bring that O minus down? Is H minus a good idea?
No.
No. How about C minus?
No.
No. How about O minus?
Yes.
Why not? O minus versus O minus.
Oh.
That's about the same stability. Why not? Poof. So it happens. Whoa. Other screen. Turning. If those electrons come back down, that oxygen takes the electrons. That's unique. Oxygen was able to take the electrons, whereas when we looked at the past unit, we had carbons and hydrogens that couldn't take the electrons. We had a species take electrons away from the molecule. That would be really cool and useful if we had, say, I don't know, named the identity of a species that takes electrons away from a molecule. And do we have such a name, John? Yeah, it's a leaving group. Right? All we've done is modified the structure, and all of a sudden it creates the potential for a leaving group. The ester has the potential for a leaving group. The ketone did not. Does that mean I get a different sequence of reactions? As long as that leaving group is the same stability or equal stability to an O-, yeah, it does. And so what happens? It continues to react. And we get a new product out of it that we didn't see before. Because now we can form an aldehyde. What's the problem with aldehydes, though? You want to field this one, Kiefer? You already provided an answer earlier.
They're reactive. They're like on the very top of the chart.
Aldehydes are more reactive than esters. Or technically actually not. But aldehydes are reactive with our H-, which then means it could react again through our past unit. So what we would have to be thinking back to is our activity rung of reactivity, or activity rung of reactivities. Did I just say that? I did say that. Aldehyde, actually I balked, but then I said it correctly. Aldehydes are more reactive than our esters. Okay? So once I've run this hydride nucleophile reaction once, it produces a more reactive species than our starting ester, and it now sucks up reagent. Right? So we have to keep in mind all of those chemistries. Every time we move forward, we're just looking at it and saying, what are the possible reactivities to us? Every single time. Kind of, sort of?
Sort of.
Cool. Can I delete the slide?
Yes.
Cool. Full delete. Boom.
Wait. I'm good.
Okay. So, if we push to this, we should now see what our actual question is. Draw the major organic product when the ester reacts with LiAlH4 followed by an H3O plus workup. Okay, you got this answer correct. Okay, awesome. We knew all of our reactivity of our ester, right? What was our reactivity? Cool, we had the base.
Oh, yeah.
We had the electrophile. We had the acidic hydrogen. Okay, so now we would look at our reagent and say, what does that reagent supply? Okay, how do you know it supplies hydride, John?
Because the hydrogen is on the right side of the chemical thing, and that usually indicates it's at the.
I
Is
memorized.
it a new memorization, Mike?
That's a new memorization for me.
Yeah, I just.
Is
Right.
it correct? If so, I'm gonna memorize it.
I would hesitate to have you memorize anything involving a chemical formula.
Okay. Never mind.
Okay? LiAlH4, you should have that one memorized. That's one of our common reagents. Yes, that supplies H-. Okay? What John said, I think, is right. Okay? What if you didn't memorize it?
Draw it out.
Draw it out. Look at the reactivity within the molecule.
We would have a hard time connecting the lithium in there. Okay? What charge is the lithium? Positive. What charge is aluminum? See, this is where if you'd memorized some stuff back in Gen Chem, it would be easier now because we would have had that be able to apply things out. Okay? Which is okay. You didn't have to do that because what could you have done now? Memorized it now. That's fine. Okay? So sometimes we build, sometimes we can't because we're missing those steps. You have to acknowledge where those holes are and decide what to memorize. Aluminum's a +3. Okay? If it's a +3, what do those hydrogens have to be? Those are all going to have to be negative.
So aluminum is negative.
Okay? So if we go through and assign formal charge, how do we assign formal charge?
Let me subtract for each negative.
Valence electrons minus bonds minus non-bonding electrons. What we went through and did with this minus and +3 thing was we effectively found the oxidation state for each of those elements. Okay, because we're responsible for knowing those oxidation states from Gen Chem. If you didn't, that's okay. You would have to know through your valence system with your charges. And what we would find is that AlH4 is a -1 charge. That negative charge sits on the aluminum. Is there a lone pair? No. Hard question. How do you know there is no lone pair? Emily. Indirectly, yes, not quite. How would you know there is no lone pair in your Lewis structure?
When it just show it? Or
Would it just show it? How is it shown?
in its structure?
How did we get that structure? We drew it. So if we drew it, how do you know you should or should not show a lone pair?
You see if the initial, you see if like there's any charge on the
Charge isn't going to help.
Okay.
Is it because it's an ionic bond and so it's transverse?
No. How do you know?
Hydrogen only has one electron.
Ooh, there's getting at the right idea. Hydrogen comes in with 1 electron. Aluminum comes in with 3. What you would do is draw a proper Lewis structure according to Lewis structure rules that were talked about in OChem 1. And if you draw out those Lewis structure rules, what you will find is the aluminum does not have a lone pair. We've run out of electrons to put into our drawing, so there is no lone pair. That would be our proper Lewis structure. How do we decide how that molecule then reacts? Okay. Can the aluminum, without a pair of electrons, be a nucleophile? No, because it doesn't have the lone pairs to donate. The electrons are now sitting in the bond. But now the question is, where are those electrons spending most of their time, with the hydrogen or the aluminum? That becomes a very hard question to answer, and that comes back to either knowing the reactivity of these or knowing something about the electronegativity. And if you look at the electronegativity difference between hydrogen and aluminum, guess what? Hydrogen is more electronegative. How would you know that? Two ways. You looked it up and then memorized it, or 2, someone looked it up for you and told you. Looking at the periodic table becomes questionable with electronegativity trends because where the hydrogen's located versus the aluminum, it's not going to look nice. I told you. I think I told you at least twice, both when we talked about our ketones and when we talk about the esters with the hydride nucleophiles. Because we look at the difference between lithium aluminum hydride versus sodium borohydride. You mean you should be grouping some reagents because of their reactivities? Yes. Okay? That organizational structure has to come from you. You have to create it because that's you creating brain synapse wave connections in your brain. Me just telling you doesn't help you. You have to do it. How do I know it doesn't help you? Good. Some questions we don't have to answer, right? So cool. If we did our hydride, the hydride comes in, puts it on, kicks it off, and we get our aldehyde. But Louis, you didn't say an aldehyde, and you still got it right. Why?
Sorry, I didn't say
Your answer says alcohol, not an aldehyde. Hydride comes in, kicks out the leaving group, forms an aldehyde.
well, because now we have to react it with the H3.
Bingo, we repeat Unit 2. And we do Unit 2 all over again to recognize the aldehyde reacts with lithium aluminum hydride and puts another hydrogen on. Hooray, Unit 2. It's almost like, in theory, you guys have been practicing now Unit 2 several times over. We move to the next one, which you got right. NaOH and heat followed by H3O+. Okay? What do we see when we look at NaOH? Na plus and OH minus. Awesome. How useful is Na plus, Malia? Yeah, not very useful. We can effectively ignore it. Yeah, it just floats off into solution. We don't have to stress too much about it. Okay? If you want to stress about it, join a different class. Okay? So, Paige, what do you see when you look at OH minus? You did not just drop that fancy term on this.
I didn't.
She said it's a reversible base, which is fair play. Yeah, it's a reversible base. That would be all sorts of nastiness that you didn't want to open up on this. Okay. But reversible bases would ultimately be going back and saying that our starting ester acted as an acid. Okay? And if we're referencing a reversible base, that means there would be an irreversible base, which means there would have to be at least two different acidic hydrogens. Do we have two different acidic hydrogens? No. So that it is a reversible base is not necessarily bad. It's just not useful in this case. Lauren, what do you see when you see the hydroxide, the negative hydroxide? Charge. Awesome. I did say negative, though. Trying to end run that answer. Austin, you just mumbled something? Ooh. Why do you see a nucleophile? Ah, remember that pattern? We went through and listed our acid, our base, our nucleophile, electrophile. We had those definitions and we had what was useful with them. Nucleophiles were typically negatively charged. I have a negatively charged hydroxide. Fantastic. That could act as a nucleophile. As Paige suggested, a little bit half-heartedly, because she just said reversible, what was implied behind that was that it was a base. Why was that useful? What charges are bases? Negatively charged. We try the base route. There isn't anything dealing with this reversibility issue, so we could try our nucleophile route, that one. Okay, because we have an electrophilic carbonyl. So we could push it, see what happens. When you go through and push it and see what happens, Louis is correct. We get a carboxylic acid. I thought you got this one wrong. Oh, there we go. Okay. Oof.
Yeah.
This is the big oof. Yeah, this is where your question came in.
That's the yeah.
Okay. So, this one, we have diba CH2Cl2 negative 78. Austin, I'm going to throw you under the bus. What do you see?
I don't know. I don't know what DIBAH is.
Cool.
I see.
Cody, do you know what that is?
I remember doing it before, but I don't remember it.
This isn't
I looked up the mechanism.
Isn't that just the lithium aluminum hydride, but like with the, instead of 4 hydrogens, it's 3?
Ah! Isn't this lithium aluminum hydride? How do you spell hydride? H4. There we go.
How do you spell that?
Close enough. Okay. What?
My old like a chemistry teacher made us like spell everything correctly or you got it wrong.
Yeah, I can't spell H, so it'd be a problem. I personally don't like the reference of Daiba. I think that is a bit misleading. This is pretty much strictly a memorization kind of question. Okay? How I would reformat this question is, number one, I would probably also say this die thing. Okay, but what you would see from me is die ball with an H or fuck. The thing in between the A and the H that I just drew in there. You would probably see it written that way, and you would probably also see this. Aluminum hydride. I would give you both of those pieces. Okay? Kiefer's got the right idea. We have the Al because aluminum. So if we write it out as Dibal, which most people do, I don't know why I'm seeing some institution or some books writing Diba. It's just obnoxious to me. Most people call it Dibal.
I think it's written on Wikipedia as Daiba.
Just
Let's listen to Wikipedia.
It's like,
why would I like the Dibal reference?
well, because it clarifies that that's an aluminum.
It provides an extra context that we're looking at aluminum. Why is that then useful? What's next to that aluminum? A hydrogen. And when we saw lithium aluminum hydride, how did that react?
It provided a positive hydrogen. Negative hydrogen.
A negative hydrogen. It provided a hydrogen nucleophile. So when we look at Dibal, guess what it provides?
Negative hydrogen.
A hydrogen nucleophile. Yeah. Okay, so we could go through and run our ester chemistry exactly the same. Oh, CH3. It goes through, we do our leaving group thing, all that fun jazz. If we wanted to look at the cheat mechanism, our H minus comes in, attacks, breaks open our pi bond, the electrons come back down, kick out the leaving group, and we would have as a product our H minus now connected, and we would have the ketone and our OCH3 minus. But what would a negative hydride do? Particularly in the presence of an aldehyde. It would very likely react again. And then this would take us all the way down to the alcohol. Okay? Why does that maybe feel a little bit weird to do with Daiba?
Because it only has one hydrogen on the structure.
Okay, so there's an idea. Dibal only has one hydrogen on it. Okay, it does. Okay, but could we have a species react a whole bunch of times by just adding a whole bunch more reagent? Yeah, we've done that before in the past. So not a horrible idea, but I would argue we've got an easy way to be like, nah, that doesn't work. What do you have, Aiden? What do you have?
Why would, for what?
What do you think our answer should be? We're reacting Dibal with our ester.
Yeah, so why does the, okay, yeah, what do you mean?
Just finish your why. Like I'm
So
positive
are
you've
you
got it
asking-
in there.
Are you asking why it makes, like why it reacts with the aldehyde again?
Sort of.
Why the reaction move forward?
Sort of. Do I have a reagent that does this chemistry on the far right? Gets me all the way to that alcohol.
Yeah.
Yes, lithium aluminum hydride does it. Okay? If lithium aluminum hydride does it, why do I have Dibal?
Because
There's the nail on the head. If I already have a reagent that does the chemistry already, why do I have to worry about another one? Because it does something different. It has the exact same reactivity. It's still an H-. We still have that hydrogen bonded to an aluminum. But it has to do something different. What would be the different thing? It stops. Okay? And if you're like, I know where this is going, Mike's going to ask why. Well, we are out of time today, so we don't have to worry about that. You don't need to stress about the why for this. This is one that I would highly encourage that you just memorize. Dibol reacts with esters to make aldehydes. Don't make it more complex. Okay? There are some explanation things that you could go into to explain why the chemistry is modified. Right? It's not formally aluminum hydride because it doesn't have that extra bond. Why? Probably because we don't want it to be as active. Right? Why does it have the carbon things on it? Probably because it helps to stabilize it so that it is not as active. It slows that chemistry. Why do we want it to slow? So that I can end at an aldehyde. Okay? This is actually a very interesting reaction because it takes me from the ester to the aldehyde. The aldehyde is more reactive than the ester, but dibol is a selective reagent. It only reacts with esters to make something that's more active, but then it doesn't react with it. That's kind of neat.
Is that why it's so cold?
Why is the temperature so cold? For the same reason you're trying to limit the reactivity. Okay? So you don't need to stress about the details behind the why. What you should be doing is addressing, okay, that is a reagent that you should memorize. And then if you want to rely on the chemistry of the structure, you can hope that I'll provide you that structure. But that relies on you understanding some deeper things about structure and function. Full structure is the aldehyde. Step 2, I believe, is actually just the quenching of the aldehyde. I'd have to check because that's something that you would have to memorize, and I don't have memorized. Like, quickly goes out of my brain. It looked like there was the potential. Yeah, I think that's just the quenching of the dibol. It's not loading the solution here, but I'll try and get it up here in a second so everybody can see it. There it goes. Yeah, it's just the quenching of the dibol. Everybody's like, well, what about step 2? Did you all ask about step 2 with the lithium aluminum hydride?
Yeah.
No, you didn't.
Oh, no.
But it was there also in H3O plus workup. What was the dibol workup? H3O plus. Okay? With that, we're done.